Hi, and welcome to the next lecture unit in the lecture chapter on nonlinear support vector machines, which is on the very fundamental kernel trick, which basically means we are now substituting or replacing every dot product in the dual form of our SVM soft margin program by so-called kernel functions or kernel computations between the ith and the j's observation, and therefore turning the linear machine into a nonlinear one, which implicitly maps the original data into a higher dimensional feature space. We could also do this actually in the primal, but I'll here keep it, well, I'm not sure whether it's simpler. It's, I think, more direct for us here, and therefore I will only do this here in the dual form. It's also much more common in literature, although, as I said, not necessary to do it in the dual form. Okay, so short recap. The dual soft margin SVM was exactly here this quadratic program under these box constraints and under this linear constraint here. And what we already discussed was that, hey, it could be quite nice if we could do feature generation and if we would have this feature mapping phi here, which turns our original data or feature vector x into a richer, higher dimensional, more convenient representation of our observation. And what we could now do is we could explicitly calculate this mapping here and then simply replace all instances of xi with phi of xi and of xj with phi of xj. And if we do that, I already discussed that if this mapping here is quite high dimensional, for example, a polynomial mapping which creates all monomials of a certain order, and we know this very well from having interaction and higher order effects from regular regression, then this can very quickly become computationally at least difficult or nearly infeasible. And as we will see, for the SVM we can even operate with feature mappings of infinite dimensionality if we use the kernel trick, which does exactly this mapping for us implicitly. So the whole idea or the whole intuition behind the whole thing is that if we look at this quadratic program here, these operations, depending on phi, they only occur in a very peculiar form. So we only have these phi operations here in a dot product type computation. So this optimization problem here only depends on these pairwise inner products, either of the direct representations or of the feature mapped representations. And this now allows us to exploit this through a certain trick, where instead of first mapping all of our inputs to an enriched feature representation and then computing the dot product in the enriched space, well, if we only have to compute this guy here, how about we kind of directly go for the target and try to compute this in exactly one go. And this shortcut computation is exactly what we will from now on call a kernel. So the kernel is basically a computation of a dot product in an associated feature space. And we'll from now on require certain properties of such a kernel function. So we'll usually call that a Mercer kernel. And a Mercer kernel is a continuous function which is defined on a certain space x times x. This will usually be our original feature space. We will later see that actually this space x here can basically consist of arbitrary objects and will map to R. And the function shall have two fundamental properties. First of all, it should be symmetric. That makes sense. So if that thing is something like I don't know, like a dot product. Basically, I mean, we know from elementary geometry that dot products measure angles between vectors. So in a certain sense, they also measure similarity. And the second property we need and we require from the kernel function is that it's positive definite. And by positive definite for such a function, we mean that whenever we use a finite subset of size n, so n can be 1, n can be 2, n can be 100, and then we look at the so-called induced kernel matrix or the induced gram matrix, which is nothing more than an n times n matrix where every entry in the matrix is the kernel computation between the ith and the jth element here of that set. Such a matrix must always be positive semi-definite. Okay? And that later on will also ensure that our transformed quadratic program is still convex for the kernelized support vector machine. Here are now a couple of very, very common kernels that are used in practice and in the literature. Let's start with the most simple stuff. So first of all, every constant function, which takes a non-negative value, otherwise we don't have here this positive definiteness property, is a very boring kernel which doesn't learn a lot. The next more interesting kernel is just the standard inner product. So x transposed x tilde, we call that the linear kernel. And if we use that, we have not changed our SVM program at all, right? So this just keeps inner products in the same form as they were before. And we very obviously now call this the linear kernel and the linear SVM. And this gives rise to hyperplanes. So from now on, I'll use this, arrow-shaped little example here to visualize also how the decision boundaries of such an SVM look like if we use the discussed kernel here on the slide. So, and for this guy here, we get a very, very simple, in this case, even access parallel linear decision boundary. Now here's a construction rule, or actually a couple of construction rules, which are good to build more complex kernels from simple ones. So first of all, we can multiply every function where we already know that it is a kernel by a non-negative constant, and then this product here, or this this constant times the kernel is still a kernel. We can also add two kernels together where we know that these are kernels, and then the resulting sum is still a kernel. Call that a sum kernel. Or we can also produce a product kernel where we, multiply two already established kernels to generate a new one. And this rule, of course, also tells us that if we take a K1 kernel to the nth power, that will also give rise to a kernel. And you can easily prove this by just still checking that the resulting induced gram matrices are still positive semi-definite for all cases. This is not really hard to do for all of these construction principles. Please try this with pen and paper yourself. And the next, or I should probably say the first interesting kernel we are discussing here now is the so-called polynomial kernel, which is of this structure here. So this is x transposed times x tilde plus some non-negative value b, which usually is set to 1. And then this thing here to the dth power. And such a kernel, first of all, is a kernel, which you can easily check by using our sum and product rules. So first of all, we know that this guy here is a kernel, because that's the linear kernel. We know that b is a constant kernel, so the sum here is again a kernel, and if we take this to the dth power, because of the product rule, we again know that this is a kernel. And the polynomial kernel is also called the polynomial kernel because it basically creates an implicit feature mapping into a space that contains all monomials up to a certain degree. For that, we should set this b here to a non-zero value to also have monomials in there of lower degree than d. And if we basically project back into original space then a dth degree kernel will result in a dth polynomially shaped decision boundary. So for example, if D is 2, we obtain a quadratic decision boundary here in original input space. And if D is 3, we get a polynomial of degree 3 here as the shape of our decision boundary. And probably the most important kernel, which is called the radial basis function kernel, or also called the Gaussian kernel, which looks like this here. So this basically looks like a isotropic Gaussian distribution without any normalizing constant in front of it. So this is basically such a bump function here. And what this does is it basically computes the distance here between the two observations. And then, as you can see, this function here only depends on these distances. And I'll denote the distance here with an r. And then we basically enter this computed distance here in this Gaussian bump function. And this computes now the value of our kernel. So you will see this type of computation also later when we discuss Gaussian processes, where this here kind of encodes the correlation of our outputs at the two observation points, so to speak. Here we'll simply interpret this as a measure of similarity. And what I'm also already now at least mentioning is that the underlying feature map of such a Gaussian kernel is actually of infinite dimensionality. So we couldn't even compute this if we would do an explicit calculation and then simply push this into our linear SVM without the kernel trick. You can also control the width of this bump function here by this sigma or sigma squared parameter. So as you hopefully know, this here directly relates to the width of our Gaussian bump. Some people also like to write this in a slightly different form by using a gamma parameter here, which would be the inverse width of the bump function. So in this case here, gamma would obviously equal 1 divided by 2 sigma squared. And I'll discuss properties of the RBF kernel also in a later unit in more detail. So I'll keep it here simple not simple, but short, by mentioning that this can basically model arbitrary decision boundaries in input space. You can basically create arbitrarily local models of quite high resolution, where you can, in a certain sense, learn any type of decision boundary shape, up to certain requirements and technical conditions and so on. So as long as these decision boundaries are, let's put it like that, reasonably smooth, we can learn them with such an RBF kernel. So let's now do this. Let's replace here all of these regular dot products by our kernel computation between I and j. And if we do that, we arrive at such a form here. Or we could also write this now in compact matrix notation by using our gram matrix here in the middle. And you can now also directly again see that this is still a quadratic program and the rest does not change. And we can still see that this problem here is convex because we are now exactly using this property here that however k looks, it is always positive semi-definite, which means this guy here is still a convex quadratic program. And therefore, every every local minimum of that, or sorry, every local maximum is also a global one. Okay, so we now should probably also discuss how we can form predictions from such a kernelized machine. That's not directly obvious, right? I've only shown you here how you can change the dual program, then you can solve for these Lagrangian multiplier, these alpha values, but now we also have to talk about how we now form our prediction function, right, in order to predict new data points. So for the linear soft margin SVM, we always had these linear scoring functions here, so theta transpose times x plus an intercept term, and we knew from our dual analysis that the theta hat, so the optimal parameter vector, looked like such a weighted linear sum of our original data points. So we also figured out that very often this here becomes sparse, so some of these alpha I guys become 0. I don't want to discuss this here any further. More importantly, what I now want to do is how this thing changes if we now apply our feature map and connect this with our kernel computation. So after our feature map, this guy here becomes phi of x, and we have to now compute this dot product here in feature space. And again, here for the theta hat, we have to project also these xi guys here into feature space. And now what we can do is we can just simply take this representation here of theta hat and put it into this guy here, and then take a look at what happens with this dot product and simply follow the bilinear rules that dot products usually have. And we assume that these also hold in our map feature space, and then use our kernel trick again. So by that, I just mean the following quite simple thing. So as this this dot product here is linear in its first component, what we can do is we can draw the sum outside of the dot product, and we can also draw all of these constants here outside of the dot product to the left-hand side. And then we take a look at what remains, and we can see now we have exactly this form that we need for our kernel trick. So we have here mapped representations into phi space of the ith and of the x observation, and then we compute a dot product between them, and we know that we can abbreviate that thing simply by using our kernel function. So I'm using that here, and that basically gives us the required result, because now we can write f of x as this computation here with the kernel function plus an intercept. So what you can now see is that instead of forming the dot product between this, or let's put it like that. So what we now have to do is we have to, for a prediction, we have to run through all of our support vectors. So all of these guys where the alpha i's are non-zero. And then we have to take the weight of this Lagrangian multiplier alpha times the label times the kernel computation between this ith observation and the new data point, and we sum all of these up, still at the intercept, and that's our prediction. I began motivating the whole thing through the consideration of a feature generation for MNIST. So I'm going to wrap this up here a little bit by kind of doing this again. So what I can now do through this kernelization is that I can conveniently perform such a feature generation as I discussed before. So for example, using interaction effects and effects of quadratic or cubic order or even higher for quite high dimensional data. So all of this is now very well and quite efficiently computable. And actually, this is how I did this before, also in the first lecture unit, so I cheated a little bit there. I didn't really explicitly compute the feature expansion. I just already used kernels because this is equivalent to the explicit feature generation. And I just want to do this here again with a couple of more kernels that I introduced here in this unit. So again, I will run this on MNIST. Again, I'm being somewhat lazy, so I'm not doing any parameter tuning. I will again only train on 700 observations. We'll again use 1 versus 1. So that's not really being lazy. That's pretty normal. So you'll use 1 versus 1 to handle this multi-class problem. And here are a couple of results that we can compare. So take them with a grain of salt. So because we're not learning on a lot of observations, no parameter tuning and so on. But what we can see here is that by going from the linear kernel to a polynomial kernel, we at least become a little bit better. We obtain also, at least relatively here, compared to the other results, a good result with this Gaussian kernel with a low setting of the gamma parameter. You can also see that if you set the gamma parameter wrongly, then you can also obtain quite bad results. So in general, we really have to tune the SVM. We have to tune these kernel parameters. We also have to potentially consider different kernel functions. So the model selection problem for the SVM is, well, I'm not sure whether I want to say difficult, but you have to do this correctly to get appropriate results. Some final comments. So as we discussed now, this kernel trick allows us to basically turn linear machines into nonlinear ones in a quite efficient manner. So this trick that we used here to turn the linear SVM into a nonlinear one, we can also basically apply to any type of linear algorithm. For example, you could very well also kernelize logistic regression. You could also actually get a nonlinear probabilistic classifier. You can also kernelize rich regression, which basically gives you the same prediction function as for Gaussian processes. And using these linear machines in high-dimensional implicit feature spaces is A, quite efficient, and B, quite flexible. And learning now takes place in this feature space while predictions are actually computed again in our original input space. So how that works, I've explained here basically on this slide. Both the polynomial and the Gaussian kernel can be computed in linear time. So I hope that's also obvious from the formulas. And computing inner products of features is therefore much faster than computing the features themselves. So you can also ask yourself, so if I already know a good feature map, is then the kernel trick not useful for me? Well, actually, if you have a good feature map, if you know already one, right? What you could also kind of try out is then computing the associated kernel function, and by computing this dot product here, and then still using the kernel trick, and that would, as long as that kernel is efficiently computable, that might actually be a very good approach, might actually be more efficient than doing this a priori really known feature mapping in a two-step procedure by expanding and then computing with your linear machine.